Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're someone who finds comfort in cosmic questions rather than quiet stillness. Either way, you've come to the right place. Tonight, we're going to drift through one of the universe's most fundamental stories, the story of stars. Their birth, their lives, and their many different deaths. And if you find these gentle explorations help you unwind at the end of your day, consider liking and subscribing to the channel. It helps other sleepy souls find their way here too, one quiet night at a time. Now, let's begin. The nature of stars. When you look up into the night sky on a clear evening, away from the glow of streetlights and the hum of the city, you see them. Hundreds, maybe thousands of tiny points of light scattered across the darkness like diamonds thrown against black velvet. But what are they really? What is a star, fundamentally, at its core? A star is not just a light in the sky. It's not a decoration hung by some cosmic hand. A star is a massive sphere of plasma, held together by its own gravity, producing energy through nuclear fusion in its core. It is a furnace floating in space, burning hydrogen into helium and releasing the energy that makes it shine. Stars are the engines of the cosmos, the factories where almost every element in existence was forged. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created inside stars that lived and died billions of years ago. And yet, despite their cosmic importance, stars follow patterns. They have life cycles, just like living things. They are born from clouds of gas and dust. They mature, settling into long, stable lives. They age, growing larger and cooler or hotter and more volatile depending on their mass. And eventually, they die. Some fade quietly into the darkness. Others explode with a violence that outshines entire galaxies. The way a star lives and dies depends almost entirely on one thing: how much mass it has when it forms. Stars come in many sizes. The smallest are red dwarfs, tiny by stellar standards, burning their fuel so slowly they could live for trillions of years, far longer than the current age of the universe. The largest are blue supergiants, monstrous stars dozens of times more massive than our sun, burning so hot and bright they exhaust their fuel in just a few million years. And between these extremes lies a vast spectrum of stellar types, each following its own path through existence. Our sun is what astronomers call a yellow dwarf, a middle-aged star of medium mass. It's been burning steadily for about 5 billion years, and has another 5 billion to go before it swells into a red giant and eventually becomes a white dwarf. It's neither the largest nor the smallest, neither the brightest nor the dimmest. It is, in many ways, perfectly average. And yet, it is our star, the one that warms our planet, drives our weather, powers photosynthesis, and makes life possible on Earth. Without the sun, our world would be a frozen, lifeless rock drifting through the void. But the sun is just one star among hundreds of billions in our galaxy alone. And each of those stars has its own story, its own journey from birth to death. Tonight, we're going to follow that journey step by step, from the cold darkness of a molecular cloud to the strange, exotic remnants that stars leave behind when they die. We'll see how stars are born, how they live, and how they transform the universe even in death. So settle in. Let your breathing slow. Let the weight of the day fall away, because tonight we're going to watch stars being born in clouds of dust, ignite into blazing suns, age into giants, and finally meet their end in ways both quiet and catastrophic. We're going to explore the full circle of stellar existence, the life cycle of a star. Stellar nurseries. Birth from cosmic clouds. Stars are not born in the bright, open spaces between galaxies. They form in darkness, in the coldest, densest regions of space, hidden within vast clouds of gas and dust called molecular clouds. These clouds are enormous, some spanning hundreds of light years across and containing enough material to form thousands or even millions of stars. They're the nurseries of the cosmos, the places where gravity slowly gathers matter and transforms it into light. If you could see a molecular cloud up close, it would appear as a dark, wispy structure, like smoke frozen in space. It would be cold, just a few degrees above absolute zero. The gas inside would be mostly hydrogen, with traces of helium and tiny grains of dust made from carbon, silicon, and other elements. These clouds don't glow with their own light. In fact, they're so dense that they block the light of stars behind them, appearing as dark patches against the Milky Way's glowing band. But within these dark clouds, something remarkable happens. Small disturbances, perhaps a shock wave from a nearby supernova or the gravitational tug of a passing galaxy, can cause regions of the cloud to become slightly denser than their surroundings. And once a region becomes dense enough, gravity takes over. The denser parts pull in more material from around them, becoming denser still. It's a runaway process. The more massive a clump becomes, the stronger its gravity and the more material it attracts. These dense clumps are the seeds of stars. As they grow, they begin to collapse under their own weight. The gas and dust fall inward, heating up from the friction of countless particles colliding with one another. At first, this heating is slow and gradual. The temperature in the center of the collapsing clump might only be a few tens or hundreds of degrees. But as more material falls in, the core grows hotter and denser. The pressure increases, and gradually, over hundreds of thousands or even millions of years, a protostar begins to form at the heart of the cloud. A protostar is not yet a true star. It doesn't generate energy through nuclear fusion. Instead, it shines only from the heat of its collapse, the gravitational potential energy being converted into thermal energy as material falls inward. If you could see a protostar with infrared eyes, you would see it glowing softly at the center of a swirling disk of gas and dust. This disk, called an accretion disk, is made of leftover material that couldn't fall directly into the protostar. Instead, it spirals inward, orbiting the growing star like water circling a drain. The accretion disk is more than just leftover material. It's the birthplace of planets, moons, asteroids, and comets. In the cooler outer regions of the disk, dust grains stick together, forming pebbles, then boulders, then planetesimals, and eventually planets. Closer to the star, where temperatures are higher, rocky planets form. Farther out, beyond what's called the frost line, ice can condense, and gas giants like Jupiter and Saturn can gather massive atmospheres of hydrogen and helium. The formation of stars and the formation of planetary systems are intimately connected, two sides of the same cosmic process. But let's return to the protostar itself. As it continues to collapse, the temperature and pressure in its core keep rising. The infalling material compresses the center more and more. Atoms are squeezed closer together. Collisions become more violent. And eventually, after millions of years, the core reaches a critical threshold. The temperature climbs to about 10 million degrees Kelvin. At this temperature, something extraordinary happens. Hydrogen nuclei, which are just single protons, begin to collide with enough energy to overcome the electromagnetic force that normally pushes them apart. When they collide, they fuse together, forming helium and releasing energy in the process. This is nuclear fusion, the process that powers all stars. And when it begins, the protostar becomes a true star. The energy released by fusion creates an outward pressure that counteracts the inward pull of gravity. The star reaches a state of equilibrium, a balance between the force trying to crush it and the force trying to blow it apart. This balance is called hydrostatic equilibrium, and it's the defining characteristic of a main sequence star. Not every collapsing clump becomes a star. If the clump doesn't have enough mass, the core never gets hot enough to ignite fusion. These failed stars are called brown dwarfs. They glow faintly from the heat of their formation, slowly cooling over billions of years, but they never truly shine. They exist in a strange middle ground between planets and stars, not massive enough to fuse hydrogen, but too large to be considered planets. About 13 times the mass of Jupiter is the minimum needed to fuse deuterium, a heavy isotope of hydrogen, and about 80 times the mass of Jupiter is needed to sustain regular hydrogen fusion. Anything below that threshold remains a brown dwarf, a dim, lonely wanderer in the cosmic dark. But for clumps with enough mass, fusion begins and a star is born. The cloud around the newborn star is blown away by powerful stellar winds and jets of material shooting out from the star's poles. These jets, called Herbig-Haro objects, can stretch for light years, carving cavities in the surrounding cloud and revealing the young star within. Telescopes, like the Hubble Space Telescope, have captured stunning images of these jets, showing the violent, chaotic process of star formation in exquisite detail. And so, from darkness and cold, from nothing but gas and dust, a star emerges. It will burn brightly for millions, billions, or even trillions of years depending on its mass. But for now, in this moment, it is newborn, a glowing ember in the cosmic night, ready to begin its long journey through the stages of stellar life. Ignition, the dawn of nuclear fusion. The moment fusion begins is the most important moment in a star's life. It's the dividing line between a collapsing clump of gas and a true, shining star. But fusion doesn't happen all at once, and it doesn't happen easily. It requires temperatures so high and pressures so extreme that they're almost impossible to imagine. In the core of a protostar, as the temperature approaches 10 million degrees Kelvin, protons are moving at incredible speeds. They're not drifting lazily through space. They're screaming, colliding, bouncing off one another with tremendous energy. But protons are positively charged, and like charges repel. The electromagnetic force, one of the fundamental forces of nature, pushes protons apart. To fuse, two protons have to get close enough that the strong nuclear force, which operates only at extremely short ranges, can overcome the electromagnetic repulsion and bind them together. This is an extraordinarily rare event. Even at 10 million degrees, most collisions between protons don't result in fusion. The protons simply bounce off one another and fly away. But in the dense core of a protostar, there are so many protons, and they're colliding so often that eventually some of them do fuse. And when they do, they release energy. The specific process that powers most stars, including our Sun, is called the proton-proton chain. It's a multi-step process that converts hydrogen into helium. First, two protons collide and fuse, forming a deuterium nucleus, which is a proton and a neutron bound together. One of the protons has transformed into a neutron, releasing a positron and a neutrino in the process. The deuterium nucleus then fuses with another proton, forming helium-3, a light isotope of helium with two protons and one neutron. Finally, two helium-3 nuclei collide and fuse, forming helium-4 and releasing two protons back into the core to continue the cycle. Each time 4 hydrogen nuclei fuse into one helium nucleus, a tiny bit of mass is converted into energy, according to Einstein's famous equation, E equals mv squared. The mass difference is small, less than 1% of the original mass. But because the speed of light squared is such an enormous number, the energy released is tremendous. A single gram of hydrogen, if fully converted to helium, would release as much energy as burning several tons of coal. And in a star's core, billions upon billions of tons of hydrogen are being fused every second. The Sun, for example, converts about 600 million tons of hydrogen into helium every second. That might sound like a lot, and it is, but the Sun is so massive that it has enough hydrogen to sustain this rate of fusion for billions of years. It's been burning for about 5 billion years already, and it will continue for another 5 billion before it runs out of fuel. The energy released by fusion doesn't escape the star immediately. In fact, it takes thousands or even millions of years for the energy to make its way from the core to the surface. Photons, the particles of light that carry the energy, are constantly absorbed and re-emitted by atoms in the star's interior. They take a random walk, moving in one direction, getting absorbed, moving in another direction, getting absorbed again, millions upon millions of times. It's like trying to walk through a crowded room where every step forward is blocked by someone else. Eventually, you'll make it to the other side, but it takes a long time. When the photons finally reach the surface, they escape into space, carrying the star's energies out into the universe. This is the light we see when we look at stars. It's not the light of burning gas like a campfire. It's a light of nuclear fusion, energy that was generated deep in the core and has spent millennia struggling to reach the surface. The balance between the inward pull of gravity and the outward push of fusion is delicate. If fusion suddenly stopped, gravity would crush the star in a matter of minutes. If fusion suddenly increased, the star would blow itself apart. But stars are self-regulating. If the core gets hotter, fusion speeds up, producing more energy and more outward pressure. This causes the core to expand slightly, which lowers the temperature and slows fusion back down. If the core cools, fusion slows, the pressure drops, the core contracts, the temperature rises, and fusion speeds up again. It's a feedback loop that keeps the star stable for most of its life. This stable phase, where a star is fusing hydrogen into helium in its core, is called the main sequence. It's the longest phase of a star's life, and it's where the vast majority of stars spend most of their existence. Our Sun is currently in the main sequence phase, and it will remain there for billions of years to come. But not all stars have the same lifespan. The mass of a star determines how long it will live. Counterintuitively, more massive stars live shorter lives. They have more fuel, but they burn it much faster. Blue supergiant with 50 times the mass of the Sun might only live for a few million years, while a red dwarf with 1/10 the mass of the Sun could live for trillions of years. The universe is only about 14 billion years old, so no red dwarf has ever died of old age. They're still in their infancy, slowly burning their hydrogen, destined to outlive nearly everything else in the cosmos. And so, with fusion ignited and equilibrium achieved, a star settles into its main sequence life. It shines steadily, converting hydrogen into helium day after day, year after year for eons beyond human comprehension. It is a beacon in the darkness, a monument to the power of gravity and the fundamental forces that govern the universe. The main sequence, a star's long adulthood. The main sequence is where stars spend the majority of their lives. It's the long, stable period when they're fusing hydrogen into helium in their cores, maintaining a delicate balance between gravity and pressure. For stars like our Sun, this phase lasts billions of years. For more massive stars, it's much shorter. For less massive stars, it can last trillions of years. But regardless of the duration, the main sequence is a time of relative calm and stability. During this phase, stars are remarkably consistent. They maintain nearly constant temperatures, luminosities, and sizes. The Sun, for example, has been shining with roughly the same brightness for billions of years. It's gotten slightly brighter over time, about 30% brighter than when it first formed, but on human timescales, it's essentially unchanging. The light we see from the Sun today is very similar to the light our ancestors saw thousands of years ago, and it will be similar to the light our descendants will see thousands of years from now, assuming we're still around. The main sequence is not just a single state. It's a range of states, depending on the star's mass. Astronomers classify stars using what's called the Hertzsprung-Russell diagram, a chart that plots stars' temperatures against their luminosities. On this diagram, main sequence stars form a diagonal band running from the upper left, where hot, bright, massive stars reside, to the lower right, where cool, dim, low-mass stars live. Our Sun falls somewhere in the middle of this band, which is why it's sometimes called a yellow dwarf or a G-type star. At the hot, bright end of the main sequence are O-type and B-type stars. These are blue supergiants and giants, massive stars with surface temperatures exceeding 20,000 or even 30,000 degrees Kelvin. They're incredibly luminous, thousands or even tens of thousands of times brighter than the Sun. But they pay a price for their brilliance. They burn through their hydrogen fuel at a prodigious rate. A star 50 times more massive than the Sun might exhaust its core hydrogen in just 3 or 4 million years. That might seem like a long time, but on cosmic scales, it's the blink of an eye. In the middle of the main sequence are stars like our Sun. These are G-type and K-type stars, with surface temperatures between about 5,000 and 6,000 degrees Kelvin. They're moderate in size, moderate in brightness, and moderate in lifespan. They burn their fuel at a steady, sustainable rate, living for 10 or 12 billion years on the main sequence. These stars are particularly interesting because they're stable enough and long-lived enough to allow this complex chemistry and biology to develop on any planets orbiting them. At the cool, dim end of the main sequence are M-type stars, also called red dwarfs. These stars have surface temperatures of only about 3,000 degrees Kelvin, making them appear reddish in color. They're much smaller than the Sun, typically only 10 to 40% of its mass, and much dimmer, sometimes just 1,000th as bright. But what they lack in brightness, they make up for in longevity. Red dwarfs burn their hydrogen so slowly that they can remain on the main sequence for trillions of years. Some of the red dwarfs that formed shortly after the Big Bang are still shining today, and they'll continue shining long after stars like the Sun have died and faded away. The reason for this mass-lifespan relationship is rooted in the physics of fusion. More massive stars have higher core temperatures and pressures, which means fusion proceeds faster. They produce more energy per second, which makes them brighter, but it also means they exhaust their fuel more quickly. Less massive stars have lower core temperatures and pressures, so fusion proceeds slowly. They're dimmer, but their fuel lasts much longer. During the main sequence phase, stars don't just sit still. They rotate, sometimes rapidly. Young stars, freshly formed from collapsing clouds, often spin quickly because they've inherited angular momentum from the rotating cloud. Over time, they slow down, losing angular momentum through stellar winds, magnetic fields, and interactions with their planets. But some stars, especially massive ones, continue to rotate rapidly throughout their lives. Stars also have magnetic fields, generated by the motion of charged particles in their interiors. These magnetic fields can be quite strong, and they create complex structures on the star's surface. On the Sun, for example, the magnetic field creates sunspots, cooler regions where magnetic loops emerge from the interior. These sunspots come and go in an 11-year cycle, and they're associated with solar flares and coronal mass ejections, bursts of energy and charged particles that can affect Earth's magnetic field and even disrupt satellites and power grids. Massive stars have even more complex magnetic fields. Some, called magnetic massive stars, have field strengths thousands of times stronger than the Sun's. These fields can affect the star's structure, its rotation, and even the way it evolves over time. Understanding stellar magnetic fields is one of the ongoing challenges in astronomy. Another feature of main sequence stars is their stellar winds. All stars, including the Sun, constantly emit streams of charged particles into space. The Sun's solar wind is a thin but constant flow of protons and electrons that streams outward at hundreds of kilometers per second. This wind fills the solar system, creating a bubble called the heliosphere that shields us from interstellar radiation. Other stars have stronger winds, especially massive stars, which can lose significant amounts of mass over their lifetimes. Some massive stars lose the equivalent of several suns' worth of material before they die. For stars like the Sun, the main sequence is a time of stability and consistency, but it doesn't last forever. Deep in the core, hydrogen is being converted to helium, and as the hydrogen is consumed, the composition of the core changes. Eventually, the hydrogen in the very center of the core runs out. When that happens, fusion in the core stops. And when fusion stops, the balance that has kept the star stable for billions of years is disrupted. The core begins to contract under its own weight. The outer layers begin to expand, and the star enters the next phase of its life, the red giant phase, aging, and expansion. When a sun-like star exhausts the hydrogen in its core, it doesn't die immediately. In fact, it enters one of the most dramatic phases of its existence. With no fusion to generate pressure in the core, gravity begins to compress the helium-rich core. As the core contracts, it heats up. And as it heats up, something unexpected happens. The hydrogen in a shell around the core, which until now has been too cool to fuse, begins to fuse instead. This shell of hydrogen fusion produces even more energy than the core fusion did, and all that energy pushes outward against the star's outer layers, causing them to expand dramatically. The star swells, growing larger and larger. Its surface moves farther from the core, which causes it to cool. And as the surface cools, the star's color changes from yellow or white to orange or red. The star has become a red giant. The transformation is profound. A star like the Sun will swell to a size hundreds of times larger than it is now. It might extend all the way out to the orbit of Mars or even beyond. The inner planets, Mercury and Venus, will be engulfed and destroyed. Earth might survive, or it might not. If it does survive, it will be a scorched, lifeless rock, bathed in the intense radiation of the bloated sun. The oceans will boil away. The atmosphere will be stripped off. Everything that once lived will be reduced to atoms. But while the outer layers expand, the core continues to contract. It grows hotter and denser, squeezed by the immense weight of the material above it. Eventually, the temperature in the core reaches about 100 million degrees Kelvin. At this temperature, helium nuclei can fuse together, forming carbon and oxygen. This process, called helium fusion or the triple alpha process, provides a new source of energy. The star stabilizes again. now fusing helium in its core and hydrogen in a shell around the core. For stars like the Sun, the ignition of helium fusion is not a smooth process. The core is so dense that it's in a state called electron degeneracy. In this state, the pressure comes not from the thermal motion of particles, but from the quantum mechanical behavior of electrons. Degenerate matter doesn't respond to temperature changes the way normal matter does. So, when helium fusion begins, the core doesn't expand to regulate the temperature. Instead, the temperature skyrockets, causing fusion to proceed faster and faster in a runaway process called the helium flash. The helium flash releases an enormous amount of energy, briefly producing as much power as an entire galaxy. But almost all of that energy is absorbed by the outer layers of the star. Only a tiny fraction escapes. Within a few seconds or minutes, the core expands, the degeneracy is lifted, and the star settles into a stable phase of helium fusion. From the outside, the helium flash is barely noticeable. The star continues to shine as a red giant, apparently unchanged. The red giant phase doesn't last as long as the main sequence. For a sun-like star, it might last a few 100 million years. During this time, the star pulses and varies in brightness. It loses mass through powerful stellar winds, shedding its outer layers into space. These winds carry away a significant fraction of the star's mass, sometimes more than half of it. The lost material forms a shell of gas around the star, enriching the surrounding space with elements like carbon, nitrogen, and oxygen that were created through fusion. Eventually, the helium in the core is exhausted, just as the hydrogen was before. The core contracts again, growing even hotter and denser. But for stars like the Sun, that's as far as it goes. The core never gets hot enough to fuse carbon into heavier elements. The fusion stops. The star's days of energy production are over, but the outer layers don't know that yet. They continue to be heated by the remaining fusion in shells around the core. The star becomes unstable, pulsating violently. With each pulse, it ejects more and more material. Over thousands of years, the outer layers are completely blown away, dispersing into space. What remains is the hot, dense core, now exposed and no longer hidden beneath layers of gas. This core is called a white dwarf. Before it becomes a white dwarf, though, there's a brief, beautiful phase. The ultraviolet radiation from the hot core ionizes the ejected gas, causing it to glow in brilliant colors. This glowing shell of gas is called a planetary nebula. The name is a historical accident. When astronomers first observed these objects through early telescopes, they looked round and disk-like, similar to planets. But they're not planets at all. They're the glowing shrouds of dying stars, illuminated by the remnant core at their center. Planetary nebulae come in an astonishing variety of shapes and colors. Some are nearly perfect spheres. Others are elongated, hourglass-shaped, or bizarrely asymmetric. The shapes depend on the star's rotation, magnetic fields, and whether it has a binary companion. But all planetary nebulae are transient. Over tens of thousands of years, the gas disperses, fading into the interstellar medium. and the white dwarf at the center cools and dims, eventually becoming invisible. For sun-like stars, this is the end of the line. They don't explode, they don't collapse into neutron stars or black holes. They simply shed their outer layers and fade away, leaving behind a slowly cooling ember that will glow faintly for billions of years before finally growing cold and dark. It's a quiet end for a star that's spent billions of years shining steadily, a gentle transition from light to darkness. But not all stars die so peacefully. More massive stars have a very different fate, one that involves fusion beyond helium, runaway collapse, and explosions so violent they can briefly outshine entire galaxies. Massive stars, short lives, dramatic deaths. If a star is born with more than about 8 times the mass of the Sun, its life is very different from that of a sun-like star. These massive stars burn hotter, brighter, and faster. They live for only a few million years, a tiny fraction of the time a star like the Sun will live. But in that brief time, they transform the universe around them. Massive stars spend their main sequence phase fusing hydrogen into helium, just like lower mass stars. But they do so at a much faster rate. Their cores are hotter and denser, so fusion proceeds more rapidly. A star with 20 times the mass of the Sun might exhaust its core hydrogen in just 10 million years. A star with 50 times the Sun's mass might do so in only 3 or 4 million years. When the hydrogen in the core is exhausted, massive stars don't stop at helium fusion. They keep going. The core contracts and heats up just as in a red giant. But because massive stars have so much more mass pressing down on their cores, the temperature and pressure can reach much higher levels. When the core reaches about 200 million degrees Kelvin, carbon and oxygen begin to fuse, creating neon, magnesium, and other heavier elements. Then, as the carbon and oxygen are depleted, the core contracts again, heats up again, and ignites neon fusion at about 1 billion degrees Kelvin. Neon fusion produces oxygen and magnesium. Then, oxygen fusion begins at about 2 billion degrees, producing silicon, sulfur, and phosphorus. And finally, silicon fusion begins at about 3 billion degrees, producing iron. Each stage of fusion lasts for a shorter time than the one before. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, 1,000 years fusing carbon, a year fusing neon, a few months fusing oxygen, and only a few days fusing silicon. The fusion stages accelerate as the star runs out of lighter elements and moves on to heavier ones. The reason for this acceleration is that heavier elements release less energy per fusion reaction. Fusing hydrogen into helium releases a lot of energy. Fusing helium into carbon releases less. Fusing carbon into neon releases even less. By the time the star is fusing silicon into iron, the energy released per fusion is barely enough to support the star against gravity. The star is running on borrowed time. And then, disaster strikes. The core, now composed almost entirely of iron, cannot fuse any further. Iron is the most stable nucleus in terms of binding energy. Fusing iron into heavier elements doesn't release energy. It requires energy. The star has reached a dead end. There's no way forward. The fusion that has supported the star for its entire life simply stops. Without fusion to generate pressure, the core collapses. And it doesn't collapse slowly. It collapses catastrophically in a fraction of a second. The core, which might be about the size of Earth, compresses down to a sphere only a few kilometers across. The density skyrockets. Atoms are crushed together so tightly that electrons are forced into the nuclei, combining with protons to form neutrons. The core becomes a solid ball of neutrons, the densest form of matter that can exist without collapsing into a black hole. The collapse releases an enormous amount of gravitational potential energy, enough to power the explosion that follows. As the core collapses, it forms a shock wave that moves outward through the star. This shock wave heats and compresses the material it encounters, reigniting fusion in the outer layers. Elements heavier than iron, which cannot be created through normal fusion, are created in the intense heat and pressure of the shock wave. Gold, platinum, uranium, and all the other heavy elements are forged in these final moments. The shock wave reaches the star's surface and blows it apart. The outer layers are expelled into space at speeds of tens of thousands of kilometers per second. The star becomes, for a brief time, one of the brightest objects in the universe, shining with the light of billions of suns. This explosion is called a supernova. Supernovae are among the most powerful events in the cosmos. In a matter of seconds, a single dying star can release as much energy as the Sun will produce over its entire 10 billion-year lifetime. The explosion is so bright that it can be seen from billions of light-years away, visible even in daylight if the star is close enough. Historically, several supernovae have been observed with the naked eye, appearing as new stars in the sky that slowly faded over weeks or months. The explosion disperses the star's material into space, enriching the interstellar medium with heavy elements. These elements mix with clouds of gas and dust, and eventually, they are incorporated into new generations of stars and planets. Everything on Earth that's heavier than helium, from the iron in our blood to the silicon in rocks, was created in the cores of massive stars or in supernova explosions. We are, quite literally, made of stardust. But the explosion is not the end of the story. At the center of the expanding debris cloud, something remains. The collapsed core, now a ball of neutrons, survives the explosion. Depending on its mass, it becomes either a neutron star or, if it's massive enough, a black hole. Supernova, the most violent explosion. A supernova is not just an explosion. It's a transformation of matter and energy on a scale almost beyond comprehension. In the space of a few seconds, a star that might have been shining steadily for millions of years tears itself apart, releasing more energy than our Sun will produce in its entire lifetime. The mechanics of a supernova are complex and not yet fully understood, but the basic process is clear. When the iron core of a massive star collapses, it falls inward under its own gravity at speeds approaching 1/4 the speed of light. The collapse is so rapid and so violent that it overshoots equilibrium. The core compresses beyond the point where it can support itself, then rebounds, like a spring being compressed and released. This rebound generates a shock wave that propagates outward through the star. At first, the shock wave is powerful, but as it moves through the dense layers of the star, it loses energy. For a brief moment, it stalls, trapped in the outer core. This is a critical moment in the supernova. If the shock wave stalls for too long, it will dissipate, and the star will collapse into a black hole without producing a visible explosion. But something revives the shock wave. Neutrinos, ghostly particles that barely interact with matter, stream outward from the collapsing core in enormous numbers. Normally, neutrinos pass through matter as if it weren't there. But the collapsing core produces so many neutrinos, and the material above the core is so dense that a small fraction of the neutrinos are absorbed. This absorption deposits energy into the stalled shock wave, reviving it and driving it outward again. The revived shock wave surges through the star, heating and compressing the material it encounters. This heating is so intense that it triggers explosive fusion in the outer layers. Elements that couldn't fuse during the star's normal life, like silicon and sulfur, suddenly fuse into iron and nickel in a matter of seconds. And in the extreme conditions of the shock wave, fusion proceeds beyond iron, creating all the heavy elements up to and beyond uranium. This is where the universe's heavy elements come from. Every atom of gold, silver, platinum, and uranium was created in a supernova. These elements cannot be made in the steady fusion that powers normal stars. They require the extreme temperatures and pressures of an exploding star. And when the explosion is over, these elements are scattered into space, where they mix with the interstellar medium and eventually become part of new stars, planets, and even living organisms. The explosion propels the star's outer layers into space at tremendous speeds. The expanding shell of gas, called a supernova remnant, can reach velocities of 30,000 kilometers per second, about 10% the speed of light. As this shell plows through the surrounding space, it creates a shock wave in the interstellar medium, compressing clouds of gas and triggering new rounds of star formation. In this way, supernovae not only create heavy elements, but also help to create new generations of stars. Supernova remnants are beautiful, chaotic structures. They glow in many different colors depending on the elements they contain and how those elements are ionized by the shock waves and radiation. The Crab Nebula, the remnant of a supernova observed by Chinese and Arab astronomers in the year 1054, is one of the most studied objects in the sky. It's a tangled web of glowing filaments, powered by a rapidly spinning neutron star at its center. The supernova remnant Cassiopeia A, the remains of a star that exploded about 350 years ago, is another famous example. It's a complex, beautiful structure that astronomers study to understand the physics of supernovae. Not all supernovae are the same. Astronomers classify them into different types based on their spectra and light curves, the way their brightness changes over time. Type 1 supernovae occur in binary systems where a white dwarf accretes material from a companion star until it reaches a critical mass and explodes. Type 2 supernovae, which we've been discussing, occur when massive stars collapse at the end of their lives. There are further subdivisions within these categories, each revealing different details about the stars that exploded and the processes that drove the explosions. Supernovae are also important tools for cosmology. A specific type of supernova, called a Type 1a supernova, occurs when a white dwarf explodes, and these explosions have remarkably consistent peak brightnesses. By measuring how bright a Type 1a supernova appears from Earth and comparing it to its known intrinsic brightness, astronomers can calculate its distance. This technique has been used to measure distances to galaxies billions of light-years away, and it was key to the discovery that the universe's expansion is accelerating, driven by a mysterious force called dark energy. But perhaps the most important legacy of supernovae is what they leave behind. At the center of the expanding debris, where the star's core collapsed, a remnant remains. And that remnant is one of the strangest objects in the universe. Stellar remnants, white dwarfs. For stars like our Sun, the end of the line is a white dwarf. After shedding its outer layers as a planetary nebula, what remains is the hot, dense core, composed mostly of carbon and oxygen. This core is no longer generating energy through fusion. It's simply radiating away the residual heat from its formation, slowly cooling over billions of years. White dwarfs are remarkable objects. They're roughly the size of Earth, about 12,000 kilometers in diameter, but they contain about half the mass of the Sun. That makes them incredibly dense. A single teaspoon of white dwarf material would weigh several tons on Earth. The atoms in a white dwarf are packed so tightly together that they're in a state called electron degeneracy, where quantum mechanics prevents the electrons from being compressed any further. Electron degeneracy pressure is not the same as normal thermal pressure. It doesn't depend on temperature. It's a purely quantum mechanical effect arising from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. When electrons are squeezed into a small space, they're forced into higher and higher energy states, and this creates an outward pressure that resists further compression. This pressure is what supports a white dwarf against gravity, but electron degeneracy pressure has a limit. If a white dwarf's mass exceeds about 1/4 times the mass of the Sun, a threshold called the Chandrasekhar limit, the pressure can no longer support the star. The electrons are forced into the nuclei, combining with protons to form neutrons. The star collapses into a neutron star. This is what happens at the core of a supernova, but it can also happen to a white dwarf if it accretes enough mass from a companion star in a binary system. Most white dwarfs, though, are well below the Chandrasekhar limit. They're stable, slowly cooling remnants that will glow faintly for trillions of years. When a white dwarf first forms, its surface temperature can be over 100,000 degrees Kelvin, hot enough to glow brilliant white or even blue, but with no fusion to replenish the heat. The white dwarf cools. Over billions of years, it fades from white to yellow to red and eventually to black. The coolest white dwarfs we've observed are still relatively young, only a few billion years old. They're dim and hard to detect, but they're there, scattered throughout the galaxy. Eventually, after trillions of years, all white dwarfs will cool to the point where they no longer emit visible light. They'll become black dwarfs, cold, dark spheres drifting through space. But the universe is only about 14 billion years old, not old enough for any black dwarfs to have formed yet. The coolest white dwarfs we know of are still warm enough to glow faintly. White dwarfs don't just sit alone in space. Many of them are in binary systems, orbiting companion stars. In some cases, the companion is another white dwarf. In others, it's a normal star or even a red giant. If the companion is close enough, the white dwarf can pull material off the companion through its strong gravity. This material forms an accretion disk around the white dwarf, spiraling inward and eventually falling onto the surface. When material falls onto a white dwarf, it doesn't just pile up. The material is compressed and heated by the white dwarf's gravity. If enough material accumulates, the temperature and pressure at the base of the accreted layer can become high enough to ignite fusion. The result is a sudden, explosive burst of fusion that blows the accreted material into space. This is called a nova, not to be confused with a supernova. Novae are much less powerful than supernovae. They don't destroy the star. They just blow off the accreted material, leaving the white dwarf intact. The white dwarf can then accrete more material and undergo another nova. Some white dwarfs have been observed to undergo novae repeatedly, erupting every few years or decades. These are called recurrent novae. But if a white dwarf accretes enough material to push its mass over the Chandrasekhar limit, something more dramatic happens. The entire white dwarf undergoes runaway fusion, converting carbon and oxygen into heavier elements in a matter of seconds. The white dwarf is completely destroyed in a Type 1a supernova, leaving nothing behind. These explosions are some of the most powerful events in the universe, and they're important for understanding cosmology because of their consistent peak brightnesses. White dwarfs are the final state for the vast majority of stars, including our Sun. About 97% of all stars will end their lives as white dwarfs. They're not dramatic or violent in their deaths. They simply fade away, cooling slowly over eons, silent monuments to the stars they once were. Neutron stars, the densest objects. When a massive star collapses in a supernova, and the remnant core is between about 1.4 and 2.1 times the mass of the Sun, the result is a neutron star. These objects are among the strangest in the universe, pushed to the very limits of what matter can do. A neutron star is almost exactly what it sounds like. A star made of neutrons. When the core of a massive star collapses, the pressure becomes so intense that protons and electrons are forced together, combining to form neutrons. The result is a sphere of neutrons packed as tightly as the nucleus of an atom. Imagine taking all the protons and neutrons in the nucleus of an iron atom and spreading them out over a sphere 20 kilometers across. That's roughly the density of a neutron star. To put it another way, a single teaspoon of neutron star material would weigh about 1 billion tons. That's as much as a mountain on Earth, compressed into a space the size of a sugar cube. If you could somehow bring a teaspoon of neutron star material to Earth, it would instantly fall through the ground, through the Earth's crust and mantle, and continue falling until it reached the center of the planet. Neutron stars are small, typically only about 20 to 25 kilometers in diameter, roughly the size of a city, but they contain more mass than the Sun. They're so dense that their gravity is extraordinarily strong. The escape velocity from a neutron star's surface is about half the speed of light. If you could stand on the surface of a neutron star, which you couldn't because the gravity would instantly crush you into a thin layer of atoms, you would weigh billions of times more than you do on Earth. The structure of a neutron star is layered. On the surface is a thin crust, maybe a kilometer thick, made of atomic nuclei and electrons. Below the crust is a region where neutrons and protons coexist, though neutrons dominate. Deeper still is the outer core, a superfluid of neutrons that flows without friction. And at the very center is the inner core, where the properties of matter are still uncertain. Some physicists think the inner core might contain exotic forms of matter, like quark matter or strange matter, but we don't yet have enough data to know for sure. Neutron stars are also incredibly hot when they first form, with surface temperatures of over 1,000,000 degrees Kelvin. But like white dwarfs, they cool over time, radiating their heat into space. Unlike white dwarfs, though, neutron stars have other sources of energy that can make them visible for much longer. Many neutron stars have extremely strong magnetic fields and rapid rotation, and these properties make them visible as pulsars. A pulsar is a neutron star that emits beams of radiation from its magnetic poles. As the neutron star rotates, these beams sweep across space like the beam from a lighthouse. If one of the beams happens to point toward Earth, we detect a pulse of radiation. The pulses are incredibly regular, sometimes as precise as atomic clocks. Some pulsars pulse once per second. Others pulse hundreds of times per second. These are called millisecond pulsars, and they're thought to have been spun up by accreting material from a companion star. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student working with radio telescopes. She noticed a strange, regular signal in her data, pulsing every 1.337 seconds. At first, she and her advisor, Antony Hewish, jokingly called it LGM1 for Little Green Men, because the signal was so regular it seemed almost artificial. But when they discovered more pulsars, each with its own unique period, they realized it was a natural phenomenon. The discovery earned Hewish the Nobel Prize, though many astronomers believe Bell Burnell should have shared it. Not all neutron stars are pulsars. Some have magnetic fields that are aligned with their rotation axis, so their beams don't sweep across Earth. Others have magnetic fields that have decayed over time, so they no longer emit strong beams. But all neutron stars are pulsars in principle, at least for some observers in the universe. A subset of neutron stars has magnetic fields that are even stronger than usual. These are now called magnetars, and they have the strongest magnetic fields known in the universe, up to 1 trillion times stronger than Earth's magnetic field. The magnetic field of a magnetar is so intense that it warps the structure of atoms and can cause spontaneous bursts of X-rays and gamma rays. Magnetars are thought to be responsible for some of the most energetic events in the universe, including soft gamma repeaters and anomalous X-ray pulsars. Neutron stars are also important for testing the limits of physics. They have such extreme densities, temperatures, and magnetic fields that they push our understanding of matter and energy to the edge. Studying neutron stars helps physicists understand nuclear physics, the behavior of matter at extreme densities, and the nature of gravity in strong fields. In recent years, neutron stars have become famous for another reason. When two neutron stars orbit each other, they lose energy by emitting gravitational waves, ripples in spacetime predicted by Einstein's general theory of relativity. Over millions or billions of years, the two neutron stars spiral closer together, losing energy faster and faster. Eventually, they collide and merge, producing a kilonova, a burst of light and heavy elements that can be seen across the universe. The first confirmed detection of gravitational waves from a neutron star merger occurred in 2010, and it was accompanied by observations across the electromagnetic spectrum, from radio waves to gamma rays. This event marked the beginning of a new era in astronomy, one where we can observe the universe not just with light, but with gravitational waves as well. Black holes. When gravity wins completely. If the remnant core of a collapsing star is more than about 2 times the mass of the Sun, even neutron degeneracy pressure isn't enough to stop the collapse. The core continues to shrink, compressing beyond the density of a neutron star. At some point, the escape velocity from the surface exceeds the speed of light. Once that happens, nothing, not even light, can escape. The object has become a black hole. Black holes are perhaps the most mysterious objects in the universe. They're not made of matter in any conventional sense. They're regions of spacetime where gravity is so strong that it warps spacetime itself into a kind of trap. Anything that crosses the boundary around a black hole, called the event horizon, is pulled inexorably inward toward the singularity at the center, a point of infinite density where the known laws of physics break down. From the outside, a black hole is defined entirely by its mass, its electric charge, and its angular momentum. These three quantities, and only these three, determine everything about the black hole. Two black holes with the same mass, charge, and spin are indistinguishable, even if they formed from completely different stars. This is sometimes summarized by the phrase, "black holes have no hair," meaning they have no additional features or details. The size of a black hole's event horizon is determined by its mass. For a non-rotating black hole, the radius of the event horizon, called the Schwarzschild radius, is about 3 kilometers for every solar mass. So, a black hole with 10 times the mass of the Sun would have an event horizon about 30 kilometers across. That might seem small, but remember, this is the boundary beyond which nothing can escape. Inside the event horizon, all paths lead toward the singularity. There's no way to turn around, no way to stop falling inward. What happens at the singularity is unknown. General relativity predicts that the density becomes infinite and the curvature of spacetime becomes infinite, which suggests that our current theories break down. Most physicists believe that a more complete theory of quantum gravity, which unifies general relativity and quantum mechanics, will be needed to understand what really happens at the center of a black hole. From the outside, though, we can study black holes by watching how they affect their surroundings. Black holes don't emit light, but they do exert gravity, and they can pull material off nearby companion stars. This material forms an accretion disk around the black hole, spiraling inward and heating up from friction. The inner parts of the accretion disk can become so hot that they emit X-rays, making the black hole visible to X-ray telescopes. Many stellar mass black holes have been discovered this way, by looking for X-ray sources in binary systems. Black holes can also be detected through their gravitational effects. If a black hole is part of a binary system, its gravity causes the companion star to orbit around it. By measuring the orbit of the companion star, astronomers can infer the mass of the unseen object. If the mass is too high to be a neutron star, it must be a black hole. In recent years, gravitational wave observatories like LIGO and Virgo have detected dozens of black hole mergers. When two black holes spiral together and merge, they emit powerful gravitational waves that can be detected across the universe. These observations have confirmed many predictions of general relativity, and have taught us a great deal about the population of stellar mass black holes in the universe. One of the strangest predictions about black holes comes from quantum mechanics. In 1904, Stephen Hawking showed that black holes aren't completely black. They emit a faint radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation is incredibly faint for stellar mass black holes, far too faint to detect with current technology. But over unimaginably long timescales, perhaps 10 to the power of 7 years or longer, a black hole would lose all its mass to Hawking radiation and evaporate completely. This raises a profound question. If a black hole evaporates, what happens to the information about the matter that fell into it? Quantum mechanics says that information cannot be destroyed, but general relativity says that anything that falls into a black hole is lost forever. This apparent contradiction is called the black hole information paradox, and it's one of the deepest unsolved problems in theoretical physics. For now, black holes remain mysterious. They're the ultimate victory of gravity over all other forces, regions where space-time itself is bent to the breaking point. They're the final resting place for the most massive stars, the end of a journey that began in a cold, dark cloud of gas billions of years ago. The cosmic legacy. Stars as creators, stars are not just lights in the sky. They're not just objects to be studied and cataloged. They're engines of creation. Cosmic factories that take simple hydrogen and helium and forge them into the rich tapestry of elements that make up the universe. When the universe began, about 13.8 billion years ago, it was almost entirely hydrogen and helium, with trace amounts of lithium. That's it. No carbon, no oxygen, no iron. All the heavier elements, everything from lithium to uranium, were created inside stars. This process is called nucleosynthesis, and it's one of the most important processes in the history of the cosmos. During a star's main sequence phase, hydrogen is fused into helium. In red giants and massive stars, helium is fused into carbon and oxygen. In the cores of massive stars, carbon, oxygen, neon, and silicon are fused into heavier elements up to iron. And in supernova explosions, the intense heat and pressure create elements heavier than iron, all the way up to uranium and beyond. Every atom in your body, except for the hydrogen, was created inside a star. The carbon in your DNA the nitrogen in your proteins, the oxygen you breathe, the calcium in your bones, the iron in your blood. All of it was forged in stellar cores or supernova explosions billions of years ago. You are made of stardust, not metaphorically, but literally. The atoms that make up your body once dwelled in the heart of a star, and when that star died, those atoms were scattered into space, where they eventually became part of the cloud that formed our solar system. This is one of the most profound realizations in all of science. We are not separate from the universe. We are part of it, woven from the same material as stars and planets. The iron in our blood is the same iron that was created in a supernova explosion billions of years ago. The oxygen we breathe was once part of a dying star's outer layers. We are the universe looking back at itself, made of stellar ashes, contemplating the stars that gave us birth. The cycle of stellar birth and death is also a cycle of chemical enrichment. The first stars in the universe, formed from primordial hydrogen and helium, had no heavy elements. They couldn't form rocky planets. They couldn't support complex chemistry. But when they died, they enriched the surrounding space with the elements they created the next generation of stars, formed from gas that was slightly enriched with carbon, oxygen, and other elements. And when those stars died, they enriched the gas even further. Over billions of years, the interstellar medium has become steadily richer in heavy elements. Our Sun is a third or fourth generation star, formed from gas that had already been processed through multiple cycles of stellar birth and death. The planets in our solar system, including Earth, are made almost entirely of heavy elements created in earlier generations of stars. Without the chemical enrichment from earlier stars, Earth would not exist, and neither would we. This cycle continues today. Stars are still forming in molecular clouds, using material enriched by earlier generations. And stars are still dying, scattering their elements into space to be incorporated into the next generation. The universe is a vast recycling system, endlessly transforming matter and energy, creating complexity from simplicity, turning hydrogen into stars, into planets, into life. And it all happens because of stars, because of gravity, because of fusion, because of the simple fact that when you squeeze hydrogen hard enough and long enough, it turns into helium and releases energy. Everything that follows, the formation of planets, the emergence of life, the evolution of intelligence, all of it traces back to the life cycles of stars. Closing, our place in the stellar story. We've journeyed through the full life cycle of a star, from its birth in a cold molecular cloud to its death as a white dwarf, neutron star, or black hole. We've seen how stars form, how they live, and how they die. We've explored the different paths that stars take depending on their mass, from the quiet fading of sun-like stars to the violent explosions of massive stars. But perhaps the most important lesson is this: we are part of this story. Not observers standing outside looking in, but participants, made of the same matter that stars create and destroy. Every breath you take contains oxygen atoms that were once in the core of a dying star. Every beat of your heart is powered by iron atoms created in a supernova billions of years ago. The calcium in your bones, the phosphorus in your DNA, the carbon that forms the backbone of every molecule in your body, all of it came from stars. You are a temporary arrangement of stellar ashes, gathered together on a small planet orbiting an average star in an unremarkable part of the galaxy. You exist because stars lived and died, because they fused hydrogen into helium, and helium into carbon, and carbon into everything else. You are the universe experiencing itself, a collection of atoms that can think and feel and wonder about the stars that made them. And somewhere out there, right now, stars are being born. In cold, dark clouds scattered across the galaxy, gravity is gathering matter, compressing it, heating it, preparing to ignite fusion. New suns are emerging from the darkness, and with them, perhaps, new planetary systems, new worlds where complexity might arise. And somewhere out there, stars are dying. Red giants are shedding their outer layers, forming glowing planetary nebulae. Massive stars are collapsing, exploding, scattering their elements across space. White dwarfs are cooling slowly in the dark. Neutron stars are spinning silently, their beams sweeping through empty space. Black holes are pulling matter across their event horizons, warping space-time itself. The cycle continues. It's been continuing for over 13 billion years, since the first stars formed in the young universe. And it will continue for trillions of years more, until the last stars burn out and the universe grows cold and dark. But for now, in this moment, stars shine. They burn brightly, fusing hydrogen, creating elements, warming planets, lighting up the night sky. Our sun will continue to shine for another 5 billion years. It will eventually swell into a red giant, engulfing the inner planets. It will shed its outer layers, forming a planetary nebula. And it will leave behind a white dwarf that will cool for billions of years, a faint ember in the darkness. But that's far in the future. For now, the sun shines steadily, just as it has for billions of years, powering life on Earth, driving the cycles of weather and climate, warming our days and lighting our skies. And you, here in this moment, are part of that story. You are stardust, temporarily gathered together, briefly conscious, wondering about your origins. You're looking back across billions of years, tracing your lineage to the stars that created the atoms in your body. You're contemplating the vast cycles of cosmic time, the slow unfolding of matter and energy that brought you into existence. So, when you look up at the stars tonight, remember what you're seeing. You're not just looking at distant lights. You're looking at the past, present, and future of the cosmos. You're looking at the engines that created you, the furnaces that forged your atoms. You're looking at your ancestors, scattered across the sky, shining down on you. And if you've enjoyed this journey through the life cycles of stars, if these cosmic explorations have helped you end your day with wonder instead of worry, consider liking this video and subscribing to the channel. It helps other curious minds find their way here too, one starry night at a time. For now, rest well. Let your thoughts drift gently like clouds across a night sky. Let the weight of the universe settle softly around you, not as a burden, but as a comfort. You are made of stars. You are a way for the cosmos to know itself, and tomorrow, when you wake, the sun will rise again, burning bright, fusing hydrogen, creating the light that makes life possible. Sleep well. Dream of nebulae and supernovae, of stars being born and stars dying, of the great cosmic cycles that turn on timescales beyond imagining. And know that you are part of it all, a small but precious piece of the universe's long story. Good night.